Hello students, in this video we'll prove Harnack's inequality for non-negative harmonic functions in the plane. Let's be given a non-negative harmonic function, u, which maps omega into r, okay, but it's non-negative, right? It's not negative. And what can I assume? And let's assume that u is continuous up to the boundary, right? So u is continuous everywhere. Good. Recall the Poisson kernel PR theta, which is 1 minus r squared over 1 minus 2r cosine theta plus r squared, is a non-negative, right? Is a non-negative harmonic function too. Okay. Of course, I can rescale the Poisson kernel, which we want to do next, right? So note, of course, that if we look at P of r over r capital, where r capital is bigger than little r of theta, you can replace little r with r over r capital, right? And then this becomes r squared minus r squared over 1, or r capital squared. So that's going to mean r capital squared minus 2r r cosine theta plus r squared, like that. Excellent. So that's the Poisson kernel on a larger disk, right? On a disk of radius r, right? And so now, what can we do? So let's suppose that dAr closure is contained in omega, right? And now what we're going to do is we know that for any particular point inside this disk, we know that dA little r is contained in dA big R, right? Trivially. Okay? Good. So we suppose this and it's contained in there. Now what I'm going to do is I'm going to evaluate u at any point in this disk over here on that boundary disk over here using the Poisson formula, right? So by the Poisson formula, what do we get? We get that u of a plus r e to the I theta is 1 over 2 pi, the integral from negative pi to pi, of r capital squared minus little r squared over r capital squared minus 2r r capital cosine of theta minus phi plus r squared little. And now what? I didn't have to evaluate the boundary data, so I'm going to do a u of a plus r capital now, because now we're integrating over the boundary, right, of e to the I phi d phi. Okay, that's the Poisson integral formula. That's a large thing to do. But now what's the whole point over here? The whole point over here is that this is greater than or equal to 0. That's greater than or equal to 0. This is a positive expression. Great. Okay, beautiful. So it could be 0 too. We can take 0. That's not bad. Okay, but now what we're going to do is we're going to estimate this Poisson kernel. What's the largest and small it can be over here? So what can I say? So what's going to be the upper bound? Upper bound? We're going to get upper bound and the lower bound. The upper bound of P r over little r of theta minus phi, that's this expression right here, right? What's that going to be? Well, how can you make this as large as possible? You make this as large as you can make this as large as possible by making the denominator as small as possible, right? So the smallest denominator occurs when this is perfectly negative, right? So this is no more than what? This is no more than r squared minus little r squared over what? I make this as negative as possible, so that's negative 2r, right? So r squared minus 2r capital R plus r squared. This, of course, is r minus r plus r over, now it's a perfect square. That's r minus little r quantity squared. One of those factors cancels out, and you're left with what? R plus little r over r capital minus r. That's the upper bound. Let's do the lower bound. What's the lower bound going to give us? The lower bound is a similar reasoning. The lower bound is going to be what? It's going to be PR over r of theta minus phi is bigger than or equal to. I make it smaller by making the denominator bigger, right? So make it smaller by making the denominator bigger. Still a perfect square, still r minus r plus r over r plus r quantity squared. That cancels with that. And the lower bound is going to be r minus r over r plus r. So they flip like that. Great. All right, and so now what do we do? So now we can replace this. So what is u of a plus r d theta trapped between? So it's trapped between what? It's trapped between this thing over here. So in other words, we get an immediate consequence of this that tells us that, and I'll pull that constant out. So the lower bound I can pull out. So it's going to be an r minus r over r plus r, 1 over 2 pi, the integral from negative pi to pi, of just what? Of just now, I pulled that Poisson kernel out. I'm just going to have a u of a plus r e to the I phi d phi is less than or equal to, what? Less than or equal to, good. So that's less than or equal to just this thing over here, u of a plus r e to the I theta, right? Good. Less than or equal to, now I can pull that r out, so r plus r over r minus r, like that. Good. Okay, and now what? And so now what do we have? So now what do we have is the following. So now we have to do a 1 over 2 pi, the integral from negative pi to pi, of what? Of u of a plus r capital e to the I phi d phi. Okay. Now, by the mean value property, what does this tell me? These things over here are just u of a. That's u of a, and that's u of a. So now we have the exact Harnack bound, right? So we have the exact Harnack bound of what? R minus r over r plus r, u of a is less than or equal to what? Is less than or equal to u of a plus r e to the I theta, less than or equal to what? It's less than or equal to r plus r over r minus r of u of a. And this estimate over here, this double-sided estimate, is known as Harnack's inequality. So this is Harnack's inequality. Okay. Harnack's inequality is very, very useful in many, many mathematical models over here. And what it does is it allows me to bound positive harmonic functions on negative harmonic functions by simply making a trivial estimate on the Poisson kernel, right? So I'm able to do this by the virtue of the fact that this thing is positive and not negative, and so that, in other words, the signs don't get screwed up anywhere. The signs are never messed up here because everything is strictly positive, right? That's why that's essentially you assume that u is not negative, right? Because you don't want any of the signs to be screwed up here to flip these inequalities in the wrong sense, right? The wrong sense can basically mess things up a little bit. So the string of inequalities over here is valid for non-negative harmonic functions, and we'll see applications of that in further videos. Thank you very much.